Okay, so let me suggest that we all, and specifically the presenters, but everyone else is also invited, gather here, consolidate, and make a group photo for next edition of this booklets.
Well, I'm not smiling. It'll be like a football pitch.
Huh? No, but those are just additional handouts to facilitate.
I suggest I stand in front of the shortest person.
But you can pull a couple of chairs and let's.
I suggest I not stand here.
Oh, it will be the best quality because it is additional light.
Yeah, just make sure it's getting the best side.
A couple of people may want to sit down.
Take a squat.
And
We're not shooting an album cover. Oh, it's
Of course it's not.
yes.
It's like this, right? This is our latest. Check it out.
Dude, I'm like that.
Yeah, where are you looking?
Okay.
It's just like 2 days.
You want? Can you please take a photo?
We'll find the free time to come.
Low quality will be seen in the camera, but cell phones are much better.
Also?
Yeah. Because who knows which will work and which will not. Everyone is welcome to join, especially the speaker.
Okay.
You're not blocking anyone?
No.
I think you're good.
Pretend that you like Dr.
One step forward. That looks good. Phases of mind.
Would you like to join us? Okay, yeah, thank you. Let's return.
Okay,
Let's go home.
Go home now, right?
We did it.
Don't consider that we are complete with them. There will be another.
You guys missed it. Oh shoot.
Can you distribute things?
Oh, sure, I can help distribute them.
Yeah.
We got us all scared. Sends that out at 2 in the morning. Clementine.
I can't. I can't eat oranges because I get dank or so.
So
we don't.
Oh, it's kind of dangerous. He's giving us fruit during presentations. Somebody does bad, it could be an orange fly.
Yeah, next time you should bring tomatoes.
You want an orange?
Alex, this is your chance. Take up like 3 or 4 oranges and just start juggling up there.
Give me 3.
I got 2.
Give me 1 more.
Here.
I can't do more than. I can for sure do 2. 3 is a little questionable. I haven't done it in like ages.
How about you?
Surprise me.
Yeah, I'll give you dark because that's the worst flavor ever.
Caramel.
There is no caramel.
That one then.
Dark?
Sure.
Like 70?
70% cocoa. I need that cocoa.
You need that cocoa. How about you?
I'm not a fan of the dark. Apparently he needs it.
Svetlana, do you want any chocolate?
Why not?
Oh, you know the best. You don't want any. How about you, Alex?
Take it more. I'm not going to open it now.
Okay, well, here's my updated slides.
Janitor's going to come in after we're done. Why are all this sticky?
Start.
Okay, well, let's start. I'm not sure if this show will have a break in the middle. We need to finish in time before we will be kicked out of the room. So we have about a little less than a dozen presentations, 11. And please try to not extend it longer than 5 minutes.
Oh, 5 minutes for
Because there will be questions for another 5 minutes, right? So we need to finish really quick. So what are we doing? It is the last meeting for the CHEM3 CHEM364 physical chemistry, and it was exposure of the for attendees of the class for the principles to characterize materials, reactions from the basic foundations of quantum theory. And there is an idea that all this activity that is accumulated through undergraduate and graduate education is targeting real life research. And why don't we try to have a little exposure to the research at earlier stage of the career that will show to attendees why it is needed and how the knowledge can be practiced. So there will be application of the basic concepts of physical chemistry and quantum theory to like 4 types of problems. The rotational motion, first 2 chapters, the translation motion of electrons in different potentials, then oscillations or chemical reactions, the 3rd one, and the last one will be a combination of both simultaneous evolution of electronic and nuclear degrees of freedom, which is like real challenge. So the last one is most complicated. The procedure is, it will be a little ridiculous for me to tell if someone, to check if anyone never saw Microsoft Windows, but just in case. All slides are here, numbered according to the sequence and the name of presenter. So when you come up to presentation, you click. And when you want to present, you click it here. So please plan on the time for walking forward, walking backwards, and do not leave after your last word. I promise there will be some questions. From previous years, I saw many attendees who try like, conclusions, done, and I'm trying to no, stay here. Okay, so with this, I would like to invite to the stage the first brave hero, Michael Odegaard, who will tell his opinion about
angular momentum or model?
Yes, exactly.
Okay. So that is what I'm going to talk about. First off, let's talk about the model, which came from Niels Bohr. He was a Danish physicist and chemist. He developed this atomic model, and he assumed the energy states were just in integers like 1, 2, 3, just because of like the energies, 1, 2, and then 3. And so he assumed that everything was integer. But I kind of went a little bit further and fractionalized that, so like non-integer states. I'm sure he would have, but MATLAB didn't exist back then in the 20s. So I have a few movies. This is just the angular momentum with the different amount of nodes. So this is 1.5, so this would have been like 1.5. Like, play. So as you can see, it's kind of not symmetrical, and there's a lot of noise, and it looks kind of, I don't know, not good. And here's 2.45. Same. It kind of started to take shape a little bit. Still a lot of noise, and it's bigger too. 2.67. Kind of a lot of the same. Starting to get a little bit more better, I guess. I did positive and negative for 2.9, and this is showing it's really starting to take shape. So this is the positive, and as you can see, it kind of rotates clockwise. And then here's the negative, and it's the same thing, but it's kind of going counterclockwise. So that showed like the negative effect on it. And then finally, here's the integer value of 3. So as you can see, it's really symmetrical and pretty, and kind of matches the theoretical a lot better. Not really any noise. So what I took away from this is the closer, the more symmetrical it is, and the less noise, and then the negative value will change the direction of the rotation. And then along with that, the code produced the transfer potential. of an electron. So there's huge spikes. Like this is really, really, really small. Like it's basically zero. So this is kind of indicating stability. So right at the energies at 3 and 4, there's huge spikes of basically the transfer being zero. And then also I noticed, so the increase in nodes also increases the size of the radius. So another thing was like, this is 4.5 and this is 1.5. So like, as it gets bigger, it also gets more stable, along with being closer to the energy value. Yeah, it's kind of what we just kind of talked about that. And then another thing that I observed was the eigenenergy states for each amount of nodes. So this one, it just is 1.5, so the ground state is here, and then this is like the first excited. Right? And then here's 2.45. As you can see, they're coming closer. And then 2.67. And then 3.01. It just keeps getting closer and closer and closer. So from that, we observed the more nodes, lower it gets, and the ground state is the same because it's the lowest energy pulse. It's open for questions.
Okay, let's thank Michael. And what are the questions?
So, what is the main kind of idea of Bohr model, by the way?
It's just projecting. I'll go to the picture.
And what is main postulates maybe he was making?
That the stability at these different levels, it just kind of naturally goes to that because it's the lowest energy here, I believe.
Then I'm not really sure what was your reason to take in not, like you were taking, I don't know what you start with, don't remember, but you're taking like 1.5, 2.9, 2.8, up to 3, right?
Yeah.
And you call it noise, but what exactly was the purpose taking the not integer number of nodes?
Okay, so
for,
just
for,
to observe
for the waves, right?
Sorry. Yeah. So I was just taking like a wave packet and taking it into like a radial kind of view. So like kind of polarizing it, or the coordinates. So it's just kind of showing that that's how many cycles goes through. So it has to be kind of even. What was the idea is it has to be even, so it like matches up in the end. So then it's like a smooth transition as it goes around the circle. Does that kind of answer the question?
Is it standing wave?
Yeah, and then convert it.
But my understanding is that to get the quantized energy, and the main postulate of Bohr, and actually the main idea of the Bohr model, is that it provides the quantized energy for electronic levels. That energy is taken, this number, corresponding to N1, N2, N3, not in between. And for this, you need to have actually the even number, not even how it calls, the total integer number. The integer number of wavelengths.
Yeah.
And the nodes actually kind of also should be the integer number, not in between.
Yeah, that was kind of what I was looking at, was the fractionalization of that. So like what the behavior of that was.
Oh, so actually
So-
your goal was to show not quantized behavior,
Yeah.
right?
Yeah.
Kind of you were comparing the case when it's pure quantum case as electron behave in an atom versus something not really quantum in between, and this is what you call noise.
Yeah. Yep. The nodes is the width, like how many wavelengths. Yeah.
Okay.
So yeah. So it kind of proved like everything's a lot more stable when it's integer. So,
If you have integer number
Yeah.
of nodes.
yes, correct.
Okay.
More questions? Please.
So if you're saying 1.5, can you think of that as being like a superposition of 1 and 2, or is that not the right way to think about it?
That's the way I kind of thought of it. I don't know. I think.
Maybe more.
So,
Superposition of several things. If there are no more questions, I thank Michael once again. And the next presenter is Gage Winger, who will continue on the rotational motion and some aspects of it.
Okay, so yeah, this is really kind of a continuation of what he was talking about earlier there. Okay. But first we're going to talk in like how it is presented here. just in the Bohr model, we kind of have Bohr model. Just have the electron kind of orbiting the nucleus, the base. And what this does is with the negative charge on the electron as it starts spinning around, it's creating a current, which will then create a dipole as it kind of moves around. So what I'm doing with the code is just applying a magnetic field to that dipole and seeing what happens. Now, this should look pretty familiar as it is just, well, not entirely. This is at 3.01 nodes, which was the default in the code that I was given, but no fields applied just yet, so we have the eigenenergies there. Now, the way the magnetic field is implemented was the product of the magnetic field and the angular momentum was subtracted from the Hamiltonian, and that was what it was pulling from to then create the later graphs. So here we have a magnetic field of 0.0001, which I had to do because higher numbers pushed everything up and it was impossible to read. You see the splitting between these two here compared to those there. As you increase the magnetic field, what happens is the splitting becomes larger. And again, I'm just running this with several different types of nodes, not entirely necessary, but I just wanted to see what happens when you do that. The trend of the splitting remains the same, and also, as Michael said, the fields drop down a bit. Again, same case here. But then what happens is, as you increase the magnetic field, the splitting increases linearly between the, as you go between like 0.0001 and then 2 and 5 here. So what happens is, at the first level, which was, no, I want to go back. Okay, so the red and orange ones here is what I defined as being the first level. The green and purple were the second ones. So as you increase the magnetic field, the splitting between those green and purple ones increases more than the red and yellow ones does. Do you sound like that?
Excuse me, I don't see red and yellow on your screen. On your.
It was because it was from the previous graphs.
Ah.
I didn't want to make Excel try to work that hard for me. So here I have a couple of videos showing what the magnetic field does to the angular momentum here. Now, you're going to want to actually just kind of follow it along because they look almost identical, but the 0.0003 will rotate slightly faster because of the torque that is applied to the magnetic field. If I remember correctly, this one started up there and ended about here. And that one should end somewhere around there. And I had to increase the time step by quite a bit because otherwise this would be almost impossible to tell that it's actually going faster. Okay, any questions?
Okay, thank you. Any questions? I have one that was directed. I designed this question for Michael, but he disappeared too quick, so you support him. You both show this green and solid and red dashes. What are they?
Just kind of hoping he would have gone over that in his.
The green
Maybe you can help.
The green's the dash is the theoretical, and the green is like what's being traded. Or the code, right? Maybe.
Try once more.
The red's not the theoretical one.
So the wave function, is it real or imaginary?
Oh, it's the okay. So the green is the real, and the red is the imaginary.
Okay.
Yeah. That's right.
Yeah,
Okay.
that makes sense with what I was saying.
What are your units on B?
That's good because
I would assume it's atomic units.
I believe so, yeah.
So I did a quick search on going from atomic units to Tesla is 5 orders of magnitude difference. So 1 atomic unit is 10 to the 5th Tesla. So having that number is really large in Tesla.
Means you're applying huge fields.
Oh.
Yeah, so your bees are large, not tiny.
Well, they're tiny compared to what we first tried.
Okay.
Nothing showed up in those graphs.
You said that the states are degenerate when you don't have field. Can you, let's say, if I give you state number 10, can you calculate the degeneracy of the state number 10 for your circular, how you call it? It's not rigid rotor, it's a circular motion, right?
Be careful, it's a tricky question.
I feel like we may have gone over this in the spring somehow, and I've forgotten.
Well, just share your thoughts.
I feel like in theory I could, but that would require me going into more graph than I had.
Can you go back to it?
Maybe you can see
You
the
can-
degeneracy of
just-
your states just from your graph, right? Or maybe you know your degeneracy at least at lower states.
Well, when you say 10, what exactly are you referring to?
State number 10, but or you can make state number 2, whatever, any state.
Probably, but I don't know off the top of my head how.
Just show what you see on your images.
Splitting.
Splitting, but splitting of how many?
How many are splitted? 3, 5? Does it depend on the n? I mean, on the when you go higher and higher, you will have more and more
I kind of
levels
noticed you
splitted.
just kind of being pairs here, because
Here's the answer.
those two.
Here is the answer. The degeneracy is just 2, and it actually goes with plus or
Okay.
minus. And it was kind of related to the previous demonstration, your motion with plus or your motion with minus, and this is your degeneracy for the
Yeah.
circular. If you go to the
Three-dimensional.
three-dimensional spherical, then of course the degeneracy will be including also your another angle, whatever the name of this angle, azimuthal and whatever.
And it will be different degeneracy, like
2L plus 1,
yeah.
with L your angular momentum quantum number. But in this
That
case, it's
sounds-
very
that sounds
You answered correctly.
yeah. But this is for three-dimensional case. For two-dimensional case, it's really pairs. Means it's doubly degenerate. Each state doubly degenerate, independent on a number of the state.
Right.
And that's why when you apply the field, it's split it in 2.
Last chance for questions to Gage. 1, 2, 3. If not, let's thank him once again. And the next presenter is Kailyn Reed, and she's starting chapter on translational motion of electrons in exotic potentials.
Alright, I did my research on the charge transfer between the perovskite and the electron acceptor TiO2. So for a little background, this is a picture that I drew to kind of explain how this is used. So the sun emits photons, which are these rays, to a solar panel, and this is a picture of what's happening inside the solar panel. So there's a sandwich between the whole acceptor and the perovskite, the TiO2, and then the electron, which is the electron acceptor. The perovskite has multiple layers, the unoccupied layer and the occupied layer. So the electron is excited from the occupied layer to the unoccupied layer, or the unoccupied level. This leaves behind an electron hole, which is shown in the red outline of the electron. Then the electron goes from the unoccupied layer to the electron acceptor, which then has a negative charge. The hole left behind by the electron has a positive charge. This is all sandwiched between two metals, which are connected by wires, which can be connected to something like a computer, which will charge the computer, which completes the circuit. This image was provided by Landon Johnson from his prior research. This is the 1D potential curve of the hydroxyl molecule that he'd worked on. And then this shows how the potential corresponds to where the molecule is. This figure shows the eigenstate energies on the potential curve. This section right here is the energy barrier that I'll be talking about later, just for future reference. And when you excite the electron from, when I go back a picture, sorry, something that I meant to mention on this slide. When you excite the electron from the occupied level to the unoccupied level, that gives it enough energy to overcome this barrier right here, which I'll show two comparing videos that I got from that later in the presentation. So the next 3 slides will be more about my methods that I used during the simulation. So this figure shows the probability versus time of finding an electron in the perovskite. So this graph was used to find the transfer rate. This section specifically, this linear section, was used to find the transfer rate in my calculations from the electron, or of when the electron goes to the perovskite from the electron accepting TiO agent, which it's also called the electron hole recombination rate. This is a graph of the potential energy again that we saw before with all of the eigenstates, and then this red and tan line up here is the probability of finding an electron in the perovskite. Again, this section is the barrier, and at this initial momentum, this side over here is completely flat because there wasn't enough energy to overcome that barrier. This is the data that I collected in this table. So these are the initial momentums that I tried in atomic units, and then these were the transfer rates that I got from the previous probability versus time graph. The kinetic energy, which is not shown on this table, was calculated by squaring the initial momentum and then dividing that by 2 times the mass of an electron. And that kinetic energy was multiplied by a constant to find these temperatures. This K value is shown in inverse seconds, which is just the transfer rate here, converted into inverse seconds by using the conversion that 0.02 electron volts of kinetic energy corresponds to 300 degrees Kelvin. This column is the natural log of this K. And then these 2 values here were put into the Arrhenius equation to find the activation energy, and so on, these 2 for this and these 2 for that, and going down the table. So a conclusion that could be drawn from this data was that increasing the initial momentum also increases the activation energy. This is the first video that I have of a comparison. So this video, the initial momentum was set to 0. I'll play the video and then I will explain. So it's a little slow because the MATLAB was taking a video and it made it slower, so it usually happens faster than this. But the reaction shows that when the initial momentum is 0, there's not enough of energy to surpass this barrier, which means there's no product that's produced. And then this is when the initial momentum was set to 1. And here you'll see that there was enough to surpass the barrier, and that over here there's the product produced. And then this is still showing the probability of finding the electron. Any questions?
Okay, well, thank Kailyn.
What is the reaction? You're talking about the product and the reaction, but you didn't show any chemical reaction.
Sorry, I was...
And what reaction you're talking about?
The electron going from the perovskite to the electron acceptor. Sorry, it's not really a reaction. That wasn't a good word to use. It's the transfer. Yeah.
So you are talking about electron transfer, whole transfer, right?
Yeah.
So you know the electron, what is the hole?
Where's the hole on this graph?
And what is
Or-
the hole, I mean, physically, what is, we know the electron particle, and what is the hole?
The hole is when the electron goes from the occupied, here, I'll go back.
No, can you return back to your figure with showing the surface and the molecule?
This
Or
one?
whatever- Yeah, this one, right? You asking where the hole is located on a
Or like what is
system,
the
or
hole?
what is your question?
Or what is the definition of hole? I mean, what is this hole?
The hole is, so right here when the electron leaves the occupied state and it's excited to the unoccupied state, the hole is where the electron was so that a new electron can be accepted.
Then how are you transferring the hole in this case?
Yeah, I'm not researching transfer,
Hypothetically,
sorry.
how the hole can be
How
transferred?
what can be transferred?
No, because it's just empty space, right?
Yeah.
Yeah,
So
I don't know how the hole could be transferred.
what happens at the low states? Are there any electrons below? So,
Yeah, so the electrons, I believe, would be excited into the.
well, technically you can imagine if there is something pushing the, or maybe it's, if it's not the low state, then you probably have electrons above. So if electron takes this empty space from below or from above, then you create a new hole at the different level.
Right.
And this is what you can say that the hole was transferred from state 1 to state 2, right?
Okay.
So of course it's not hole which is moving, it's
Yeah.
electrons which going from one place to another way, and then your kind of vacancy
Okay.
is moving, and you can say that this is also transfer of the hole.
Okay.
I have chemistry question. What's Perovskite?
Yeah, I probably should have given a definition for that.
Again,
but
return back to your slide with with this real structure.
This, oh, wrong.
And
This
it would be good if
I
you had some
believe
color
this
scheme
is-
for your, for different atoms. So
Yeah.
do you have any ideas what these colors for which atoms they stay for?
I know we talked about which colors were which ones. I don't know if I remember correctly. I know that this is the dye and this is the perovskite.
It's not dye, right? In this case, it's CO2, and this is
Or
your type.
sorry, not dye.
It's titanium dioxide nanoparticle.
Yeah.
Titanium oxide nanoparticle. Yeah.
I believe there's.
Okay, I will help you. There should be what? There should be lead. There should be bromine or iodine or what kind of?
I think it's bromine.
Bromine. So any idea? And something else.
Cesium.
Cesium. So now you just need to figure out which one is which one.
Okay. I think these ones are the bromine. No.
I don't know.
Do you
So the lead are the tan colored ones, the cesium are the blue ones that are kind of like inside of the cages, and then the bromine are the more reddish ones.
Okay.
So that's Perovskite?
Yes.
Are there any other Perovskites? What's the term Perovskite is used?
Oh, it's a very wide term.
Yeah, I think it just means like the cage, like he kind of said. I don't know the definition. I'm sorry.
That's a specific type of the solid state with that unit cell.
What?
With that unit cell, you can have different perovskites depending on which metals you have.
Oh, okay.
So it's a type.
Like for example, cesium can be substituted by some organic ligands, right? I don't know.
Sorry, what was it?
So was it cesium? Oh no, not cesium. Something can be substituted, but another cations coming from organic cations, right?
Yes, yeah, so methyl ammonium and lead iodide is another really common one. So instead of the cesium, you have like a whole ligand just stuck in there.
And again, bromines can be probably any other halides.
Yep.
And instead of lead, anything instead of lead? No?
Not that I frequently see, but you can. I know that you can, because I think I've seen, oh shoot, what was it? I may have seen titanium in place of the lead. Oh, just T? Okay, yeah, that.
But then the efficiency drops 4 times.
Yeah, but it's not quite as toxic as anything.
More questions to Kailyn?
Just very quick question. So this is a three-dimensional structure, right?
Mm-hmm.
So what is the dimensionality of your potential has to be, and what you use for your simulation?
For the simulation, we use the 1D potential, but
Okay.
I think.
So it's kind of a projection. It's
Yeah.
exactly the projection on this layer
Yeah.
which you show.
Mhm.
But in reality, of course, it has
Right.
three-dimensional shape.
Yeah.
And very quick, another question: can you go to your initial kind of state in a potential?
This one? Or
Where you show in the wave packet or whatever the electron? Yeah, this one.
this one?
Yeah. So you said that it's not enough energy to go through this right side, right? So what is the probability at the initial moment, right, before it's actually moving anywhere? What is the probability to find the left side? This side? Yeah. Oh, doesn't matter. Yeah. What is the probability to find the electron
On titanium dioxide.
This is where titanium dioxide is.
Yes,
Yeah.
this is the titanium dioxide side, and this is the perovskite side. There's, I believe, no chance of finding it.
So zero?
Yes, if the initial
Sure.
momentum is.
It's electrons. Is the barrier infinitely large?
Yes.
Yes.
No.
It's there. You can see it.
Yeah,
Which barrier actually electrons should move through?
this one right here.
And it doesn't look like it's infinitely large barrier.
Right.
So it's a finite size barrier.
Mhm.
So, have you talked about tunneling of electrons through the finite barrier? Particle in a box.
Yes, we did.
What is the difference between classical particle and the quantum particle in a finite size box with a finite barrier? If it has less energy than the barrier. Classical particle has no way to go through the barrier if its initial energy is less than the barrier energy.
But the quantum particle would.
It can penetrate because your wave function has exponential tails, which makes not zero, it's a very small probability, but not zero probability that your electron will be outside the finite barrier. So means if you wait for very, very long time, of course you will see some electron density on the other side of your potential.
Okay, so are you saying
But
that?
initially it is zero because initial state is prepared this way, right?
Well, it depends how you prepare.
It takes time.
At the very initial moment, if it's really just localized.
So she was right.
But no, when you're solving the equation, right, your wave function should have this exponential tails, which immediately make your exponent is not having exactly zero at any x, right? Which means you will not get zero probability.
Okay, so just very, very small.
Very, very small.
Okay.
Anyone else wants to challenge Kailyn with questions? If not, thank you for once again. We have next presentation about translational motion of electrons in specific potentials. So it will be our special speaker today. So David was not taking the course, but he volunteered to make presentation. So if he performs better than anyone else, it means that there was no reason to give the course, and anyone can present it right away.
But he's a credit student, right?
Okay.
So we were looking at thin film semiconductors. So what we were modeling, we were also modeling on perovskites. And as you look at this is not the best picture, but the blue atoms here are cesiums, the pink ones are bromines, and the brownish colored ones are lead. And then we have ligands attached. We have ethyl ammonium and acetate ligands attached. And we have two different perovskites that we're looking at, and they vary in their layer setup. So they have layers of cesium and bromine and lead and bromine. So for the cesium rich perovskite, we have 4 layers of the cesium and bromine and 3 layers of the lead. For the lead rich surface, we have 3 layers of the lead and 2 layers of the cesium. So then the geometries are optimized in VASP using our first equation here. And then the second equation was used to translate the 3D potential to 1D potential. So what we found is for the lead-rich surface, we have our potential energy wells here, and this isn't the best graph. These ones where the lead is. In this graph, the lead is gray. Where the lead is where the deepest wells are. And the cesium wells and the ligand wells are approximately the same level. And then over here we showed that the dynamic effects of the electron position with time. And it starts on the ligands and moves toward the perovskite. For the cesium-rich surface, we also see the deep wells being on the lead atom, or the lead layers, and the ligands and the cesium layers are also similar in size again. And then we also see that in these ones, the potential is the electrons are moving toward the lead wells here. And so the idea is that this would indicate that there's a good chance that these would be photoluminescent, which is what Daniel was working on when the materials we were using were from Daniel's research. And what he was working on was trying to determine some of their photoluminescent properties.
It done? Okay, let's thank David. So anyone wants to challenge David with questions?
Can you explain this contour plot a bit better? Because to me, I don't understand how you can say that it's photoluminescent looking at it.
I did not include it in the presentation or in the paper there, but in Daniel's paper that we got these models from. So here's the cesium. It's actually showing a trap state on these ligands right here in the HOMO form, for the HOMO orbital. So as we look at it, the electrons are moving toward the perovskite surface.
But if it's a trap state, aren't they typically optically inactive?
Yeah.
So then wouldn't that mean that they're not luminescent even if they spatially localize?
Would it be right to say that you're exploring whether the charge carrier would prefer to move towards?
What's that?
Are you exploring whether the electron stays inside the slab or moves towards surface?
So what we were exploring was the idea was that it was moving toward the surface here. So these wells are corresponding approximately to these two layers of lead, the lead surface.
So it's still lead surface, not the organic ligands.
Yeah, not the ligands.
Is it good or bad?
That should be good.
Okay.
Very short question. You put it in atomic units. What can you transfer it at least at something which we typically use? Like,
so
what exactly these atomic units in lengths mean? Anyone knows?
Ask the class.
Is it a Bohr?
If I'm trying to remember how big the atomic unit was.
Passed this course. You got the
It actually has a physical meaning, and he was giving you a hint. So looks like people should take your course, right? At least to answer this question. Although I'm not sure that everyone knows, but I just suppose.
I remember calculating it when me and Daniel were first sitting down, but I do not remember.
What is bigger, angstrom or atomic unit of length?
Angstrom.
Bigger?
Yeah.
How much?
A little more than double, if I remember.
Okay.
It's a Bohr radius of the first electron. Bohr radius, which is actually the distance of electron from the nuclear at the first orbit, which is around half of angstrom, if you put it in the units.
Good.
Yeah, but
Good.
the physical meaning of your atomic units, in length atomic units, right, is that it's a Bohr radius.
Okay.
More questions? If no, let's thank David once again. And, last in the section about translational motion of an electron, but not last for the whole class, the presentation by Joseph Benidt, and I think he needs to teach anyone he interacts with how to pronounce his name, because there is a
Benidt.
Benidt, because there is a big temptation to tell the bandit. Okay, so.
All right, so my research was done on electron and electric field for the purpose of electrochemistry. So if my classmates can remember back to first year chemistry, it's a redox reaction. So you have one atom, another atom, electrons moving from the one atom to the other one. This one loses, it's reduced. This one gains, one is oxidized, and the oxidation states of the atoms will change. And so the hypothesis moving forward is that if you apply an electric field to this reaction, that a negative electric field will decrease the activation energy of the reaction and will increase the probability of the reaction occurring. And so this is just equations used in the theory behind how the MATLAB propagates a wave packet. I actually have a couple of videos showing the code running. So we have two different potential wells. We have the proton donor and the proton acceptor. Proton acceptor's well is twice as big, so as wave packet goes from left to right, it should progress towards that as time goes on. But this
Proton
is
or
with
electron? Proton or electron?
Electron, did I say proton? Electron. So this is with no electric field. As you see, the green line is a flat slope. And so as it goes from left to right, it's tending to go more towards the right here. But there's still a lot of electrons at the left side. So when we apply the negative electric field, what happens is when it tries to propagate to the left, it can't overcome this barrier. So then the slope pushes more of the electrons to the right side, so towards the proton acceptor. So we have a higher charge density on the right side. And so to compare that to if you put a positive electric field, as it tries to go to the right side, it cannot overcome that barrier. And so very few electrons will make it to the proton acceptor. So reaction doesn't happen much at all. The MATLAB was slow recording these and calculating it at the same time for whatever reason the other day. And so this is a probability graphs over time. Have no electric field as the control, and see at about 40% of the electrons should be on the proton acceptor side.
Electron. Not proton, electron.
In my mind, I'm saying electron.
You continue talking proton acceptor instead of electron.
I don't know why I keep saying proton.
You like protons.
I'm a positive guy, let's just say that. And so this is the best probability of reaction I got was from a negative point. This is supposed to be 0.08, not 0.8 volts. That would be too much. So then there's almost double the probability. So I think it was at a, like 0.67, 67% of the electron being on the right side. Then unpredicted by me is that if there's too much of a negative charge, those reaction probability will increase slowly, but then it'll taper back down. Because my understanding is the electric field was too powerful, so it actually escapes both the left and the right wells and doesn't stay in either atom. And then one with the very slight positive charge shows that it's 30% chance of electron being on the right side of the barrier, as opposed to no charge where it was about 40%. And this is a graphic representing the data of different voltages I used. So 0 voltage of the slope. So it's a change of probability over time or change of charge density over time. So the higher the slope, the higher the current going from left to right on the potential graph. So as it shows, you have two more powerful peaks at about 0.8. Then as you go to more increasingly strong negative fields, it goes down to 0 probability. And same thing as you head towards the right in positive values. So the results that I got supported my initial hypothesis up to a point. I didn't anticipate the stronger negative values reducing probability. And I was very happy the simulations, I got them to work without too much fuss. It's a hard part for all of us, and can be future work. There can specify it to do work with specific materials and specific reactions. And
okay,
that's it for that one.
Questions?
So maybe you can go to this figure where you're showing your curves, and there are data 1, data 2, linear, y maximum, data 3, data 4, previous one. I mean, this one.
This one?
Yep. So what does this mean, data 1, data 2? Like, what the different colors for the slides? What exactly how they are different?
Oh, this is these top two lines. I'm not sure between the difference between the red and yellow or the the blue and yellow and the red and purple. But top two lines are the probability of the electron being on the left side in the left wells, and this is the bottom two lines are the probability of the electron being on the right side of the wells.
But my question is, what's the difference between these colors? Like red and purple or something like this? Because on the other graph, it's just marked data 1, data 2. They have different initial conditions. You differently prepare your initial state, or what's really this mean?
Already same initial conditions and slightly different methods.
Sounds about right. I'm not sure. I was never exactly sure, but I always the slopes were all calculated from the red line.
Okay, still a mystery.
So it was what we discussed about a month ago, presentation by Kailyn about different representations of momentum operator for this code.
We're just using different methods, and that's why you see a little bit deviation in this behavior.
More questions? Oh, please.
So for your one-dimensional potential, what does that represent? Because there seems like 5 or 6 wells for one and 5 or 6 for the other. What does that mean?
Try, please try.
Let's go back there.
David, would you like to help?
I would
just
appreciate that.
They're kind of having some periodicity there, right?
Yeah.
Yeah.
Maybe,
Do you see any connection between your presentation and this?
maybe it somehow can be related to periodicity in a solid structure?
And Kevin, you also
Position of atoms
may help you.
in a lattice
So I'm
of
guessing
perovskites?
as it goes in between spaces in a molecular structure.
Good, very good. It's one can refine answer to like better perfectionism, but it's a good direction. So everyone is with Joseph. Can you repeat your answer?
Also, it's a potential wells is basically spaces in between the atoms and like a crystal lattice or molecular structure.
Okay, makes sense. So where the spatial location of nuclei correspond to dips in your potential.
Yes.
Okay.
And it looks like you have an interface.
Same
right?
as in
That's why
previous
they're
two talks,
different.
right?
In
Your potentials have dips where atoms were
well,
located. Right?
but in the values of depthness. So we got to have to round up.
Yeah, it was important. More questions to Joseph? If not, let's thank him once again. And Dylan Prief is the next presenter. So he starts new chapter, new section. From now on, we will start going about favorite objects of Joseph, about protons or more heavy nuclei. From now on, there will be quantized motion of nuclei or interatomic distances. And his talk will be about infrared spectroscopy, which is to some sense connected to Joseph's presentation. He will also apply electric field, but not to electrons, but to either protons or more heavier atoms.
Yeah, so I'm doing infrared absorption by just observing the harmonic oscillator. So infrared spectroscopy, basically just you're shooting an electric field at like the bonds, and then you're observing how that bond reacts. So there might not be like a high absorption, and then at other points there'll be a strong absorption, and then depending on the absorption peaks, it relates to various bonds. Okay, so it's basically a little introduction. So using infrared spectroscopy, you can identify various functional groups just by observing their absorption peaks. IR uses external oscillating electric field described in the system right here, and to basically absorb these peaks. The electric field interacts with the charges of the dipoles, causing it to oscillate back and forth. And then, so basically this equation right here describes your total Hamiltonian by your initial Hamiltonian, and then, actually the dipole, or this is your initial Hamiltonian, and then this is your dipole of the electric field, and then that changes. And then if the molecule is nonpolar, this over here should be 0, just because there's no it just doesn't oscillate, or there's no effect due to the charges of the molecule. And then, so basically this is describing the overall idea is by applying energy to this bond, it'll oscillate at different energies depending on the bonds. Frequencies, yes. So here I just have 2 video representations just describing, you'll see there's a yellow line and a red line, and then they just describe your electric and potential energies, and you can see how they're different. And this is just a value I chose, and then you'll notice this is the peak where it was observed later. I'll show you your graph, and you can see how the energy of this system is a lot higher than this system.
And the energy, you mean frequency?
Yeah, frequency.
Just in atomic units, the equivalent.
Yeah.
It's frequency, how frequent electric field oscillates.
Yes.
Okay.
Yes. So that's for you. So then you can just notice they kind of stay kind of just near each other. There's not a lot of movement compared to when the absorption peak was observed. You notice that there's a lot more energy of the system.
So it accumulates energy much quicker.
Yes.
That's a certain. Okay. We can launch both at the same time. That's cool.
Okay, so here I changed from that initial equation, I changed the omega or the W value of the energy system that was being applied. And then you can see that this is just, I varied that W value over time. And you can see that how the energy accumulates over time. And so these are just a bunch of various energy levels or frequencies. And then this 0.1 here is where you'll absorb the frequency peak, and you see that it's substantially higher than the other values.
And what is on the Y? Energy? Total energy?
Yeah, total energy.
Versus time. Okay.
Yep.
So your energy is not conserved. It's growing.
Yes. So here is my absorption peak. This was observed at 0.1, so this is where you can see that the total energy is like the highest. So that's when the bond between when you use your infrared, and you'll observe that the bond right here is at its highest. So this is useful just for observing different peaks in molecules. And then, but you can see that at other values, there's not a lot of energy until you hit this 0.1, and then it just decreases significantly. Overtone is just defined as a factor of the natural frequency. So the natural frequency in the system was determined to be a 0.1, and then in theory, there should be in each factor of the frequency, there should be what's called an overtone. And then so here is where I've observed my initial frequency, and then in theory there should be another overtone at this 0.2 value, but this was not observed. So then this is at 0.2, this wasn't observed, and then in reality, in theory, there should be another overtone at 0.3, and so on. You have any questions?
Okay, let's thank Dylan. I know who will ask questions. Okay.
So, are you only simulating a diatomic atom?
Yes.
Okay, because I don't think the approximation that says if it's a nonpolar atom, the D will always be 0,
Yeah.
which then means that you should never see IR peaks
Yeah.
in a nonpolar.
Yeah. Yeah. So we were just observing diatomic. I just didn't read that very clear.
Okay.
More questions? If no, let's thank Dylan once again and move on with the program. So, next presenter, bless you. Odegaard will continue the stories about, bless you. Gesundheit. We'll continue stories about harmonic oscillators, but he will touch a really novel area in the world science. He will try to make connection between NDSU physical chemistry course and quantum information.
So my topic was the superposition of wave functions in a harmonic oscillator. So to get a couple of things defined first, cat state is a superposition of wave functions, and it's defined with opposite and equal momentum, not necessarily equal, but usually equal momentum in a closed system. So to create a cat state, you just set up two wave functions. In this case, it was in a harmonic oscillator, and they would be about the same distance from the center apart and have equal and opposite momentum, so they would crash into each other. And then using some of this, we can put different coefficients in front of the two wave functions in order to create different cat states and demonstrate a block.
Why cat? It's not bra and cat, it's something different.
The cat is for Schrodinger's cat. It was named after that because they said they have two distinct and opposite states, life and death. And so since they have two distinct and opposite states, cat state. I didn't name it. So a little bit more background.
So Schrödinger was killing cats?
Yeah, trying to. And a qubit, a little bit more background. So this is getting into more like the quantum computing and quantum information. So a qubit is a basic unit of information in quantum computing. Much like a bit in regular computing, a bit can only have 0 and 1, whereas a qubit can have any of the values in between. And it does this by having a cat state, or just a superposition of states. So a major challenge right now is actually how to read a cat state, because as you'll see in my how to read a qubit. So as you'll see in my presentation later, there's a visualization of when the two wave packets collide with each other, and they don't necessarily have a good way of reading that in real life and to use quantum computing more. So this is, I mentioned a Bloch sphere, and this is a Bloch, is it Bloch? Bloch sphere. The two functions right here are 0 and 1. So this represents a 0 in a regular bit information, and this represents 1. So if you only had 1, like if you were in the bit, you'd only be able to either be at this point or this point. But with a qubit, you can be at any point on the surface of the sphere.
Alex, what is regular bit without Q?
It's used in regular computing that either you can have 0 or 1, and a bit is used to make up a bunch of different characters, but it only has the power to do 256 characters, the alphabet, and
byte.
some. Yeah.
Byte.
So a bit makes up a byte, which makes up more and more and more, and you can have computers right now oftentimes you'll hear the term 64-bit. That uses 64 bits in one processing unit. So continuing, so my experiment was to set up two different wave functions that, like I said, that had equal and opposite momentum. So this is the two wave functions represented. For those of you in this course, you probably recognize the little bit of wave functions because they're what we used in the original harmonic oscillator. There's some slight differences here, where this is the initial momentum of each of them. This P1 actually could be represented with a negative P0 if you so decided, but in order to make it a little more obvious, and as well as these two represent the initial positions of the wave functions. So what we did was we set that up and we let it run. In order to get them to crash into each other, however, we needed to set up an equation that had both of them in it. And these different coefficients out front are the coefficients I talked about. So by varying these, you can get different points on this block.
So your initial state is adding together two Gaussian
yes.
humps. It's like a camel with two humps.
Yeah,
okay.
so it's a camel cat state. So by changing these two coefficients, you can move this point all the way around this Bloch sphere. And in order to get the expected outcome of where these are, there's equations can be derived. It's a little bit long on how to get to these, but you can use the coefficients of 0 and 1 in order to determine where on the x-axis and where on the z-axis it is. In this experiment specifically, did I have it? No, I don't have it on the next slide. I don't have it on that slide. We decided to say that we were going to have y equal to 0, and you can do this if you, because on the sphere we automatically assume that c squared plus c0 squared plus c1 squared equals 1 in order to give the radius of the sphere. And then if you set one of them arbitrarily, one of the imaginary parts of the coefficients equal to 0, which you can assume based on this equation, you can only get half circle, because you can't go into the negative because that's imaginary for the y portion. And you can only stay in the positive. And I'll have a visualization of this later, and it'll be easier to explain. So keep going. So this is just some code from the actual experiment. So this is all the initial variables that you had to set up. Normally, for some other people, they only had P0 and X0, so they only had one wave function, but in order to set it up, you just had to add a second wave function and a second initial position. The middle was set to be 40. And then, in order to go through this, you just set up the same wave function, just with different variables, as you can note throughout the code. And something that I forgot to do when I originally made it was I forgot to actually add them together, so my code was getting a major error, and I was wondering why it was doing that. But you had to add it together. And in order to get the system to have the coefficients, I named the coefficients AGQ1 because I didn't know what variables were actually taken. I didn't want to look through the long list, so I just kind of hit my hand on the keyboard, and that's what came out. And so I also thought theta was taken, so I just changed that a little bit. And in order to change it, you just change the number in front of theta, in front of pi, in order to get a different theta, so that your sine and cosine will change the coefficients in front of it just slightly. So you can read that, but we'll get more onto the visualization since it's easier to explain. So like I said before, instead of having a sphere, we only had a half circle. So this is 0 and this is 1. And then these are different coefficients multiplied by pi. And so if you actually wanted to, and you included the imaginary units, if you went back to 0.375 pi, it would just keep going back around the circle. But note, since we're only dealing with one coefficient having imaginary units, we only had to deal with one part of the circle. Oh, pi got deleted there. Uh-oh. But by changing the theta, and this is like 3/4 over pi, half pi, regular pi, you get to have different coefficients. And this is a nice big old table to explain all of that, of course. And then using that, we can determine Sx and Sz is cut off here. But Sz will show that at this position, it'll be +1, and Sz at this position will be -1, and x will equal to 0. So now when you're actually in the wave function, when you watch them crash together, you can see the different wave functions as the probability as they go through time. So as you can see, they'll start over here and kind of go throughout. And then the C is the middle position. So you can see when they get to the middle, they crash together. And in a sec, you'll see the standing wave that they actually create. So when they come together, they create that cool little standing wave. And this right here, when they come together in the middle, is where they sometimes have trouble in reading the qubit, because when they have two different bits, when they have two different superpositions like that, it's hard for current computing techniques in order to quantify this. And so this is where people are having a lot of research trying to find information about this. Because once you have a qubit, once you can read a qubit, their computing increases by, I think it was 10,000%. So I mean, it would be very useful to have that, obviously. And so this is more of a superposition, like in the middle of like a quadrant of the sphere. So as you can see, 1 is obviously much bigger, representing that it's closer to the bottom or the top. In this case, it was actually closer to the bottom. And if I let it run, you'll see it collide once more. But then if you take out one of them completely, it just goes up and down as a normal harmonic oscillator would. And I believe that is the end.
Okay, well, thanks, Alex. So any questions about his presentation? questions. How do you create them? How does experimental setups create these superpositional states?
If I go back to the code.
Not in your modeling, but in wet chemistry or in like hard physics.
You would have to create two different bits, and bits are just an alternating of currents. So 0 is one current, and 1 is a different current. And in order to create this, you have to have two different ones. You don't actually have to have two different ones, but most of the time you have two different bits. And then in order to read it, you have both of them in the middle, and you're trying to read in between them. Because when you go from 0 to 1, the change isn't instantaneous. You can't change to 0 current to 1 current instantly. So in the middle is where they're trying to figure out how to get the qubit quantified.
Okay. Let's think about as a group and maybe try to answer this question once again after presentation by Isaiah. He may not know, but his presentation is somehow related to this procedure. Let's thank Alex once again. And we are going widely to a different research direction. So we'll move us from quantum information to biochemistry, to catalytic reaction in enzymes, stemming from physical chemistry quantum course.
Awesome, thank you, Dimitri. All right, so my experiment was look at catalytic decomposition of chloride from a particular enzyme. I just picked chloride dismutase. But really looking at that bond distance and how the rates were affected by a catalyst. Okay. So in the chemical reaction, we obviously used chloride, and with chloride, we used chloride dismutase as our enzyme, which developed molecular oxygen and chloride. Chloride dismutase contains a prosthetic group known as heme. Heme contains a metal ion called iron, and this iron is what drives the catalytic reaction forward by binding to the oxygens of the chloride. This particular reaction is pretty rare in many biological systems in that it doesn't happen very often. Most often occurs with bacteria, respirating bacteria, where they breathe in chloride and they expel molecular oxygen and chloride ion. But currently, right now, there's not very many relationships with chloride dismutase and other heme-containing proteins. So with my structures, first structure here is the chloride dismutase as itself. There are 5 different domains of biological structures with numerous alpha helices, amino acid side chains. Then the structure right next to it is the heme group as well. What's most notable is the iron in the middle, and this iron is in an oxidation state of +2. In the reaction we'll see later, it'll go to +3 once it binds to the oxygen, and then it'll go back to +2. This is more of a top view of the heme. Both above and below it are 2 amino acid side chains that do affect the states at which heme reacts. That's kind of a later topic in biochemistry. And then in the bottom here is just chloride as a structure, just as a reference. Okay, so here's my catalyst mechanism. In the first step of the reaction, we have our chloride and our heme group. And essentially we looked at how the initial momentum affected the chloride approaching the heme, which would bind to the iron, making it go to an iron 3 state. And then eventually the chloride would dissociate into hypochlorite. And this hypochlorite would eventually move far away, creating that interatomic distance, which is analyzed in this chapter. And then eventually it would come back, bind again with oxygen on that heme, and then dissociate completely into molecular oxygen and chloride. Right. And so this is kind of a look at the reaction itself. This is provided by Braden. And so what kind of happens is the oxygen binds to the iron, which is that orange, and then it dissociates later, and then this floating off in the distance is the hypochlorite And the rest of the reaction would pursue as normal in the method. So the method we did this was by almost any other method. We did a wave packet propagation in MATLAB, which then evolved by the time evolution operator, and we obtained time dependent potential data by looking at the cross-sectional areas of the reaction and taking the integration values of those for probability. And then continuing on, we found the rate by using those reaction probability distributions to eventually get into our Arrhenius equation, which showed us the activation energy developed in this reaction. And so this is the wave packet simulation as itself. The red and blue simulates the reactants, and then the green here is the kind of the energy barriers itself. So this is this first peak here is the first energy barrier, and then this is the second peak. And so what we'll find out is as it proceeds, it's kind of fast, but what happens is as it approaches the energy barrier, some product will be formed. So some will surpass the energy barrier, and then some will stay back and then continue on. What was most notable was when we did low values of initial momentum, not a lot of the reactant surpassed the activation barrier, but more so what happened was quantum tunneling happened, and we noticed that some of the product was created, but very, very small amounts. But so again, as we get higher initial momentum values, more product was created and surpassed that energy barrier. And so here's kind of the data representing this. So this is just a sample of the potential data I was provided by Braden. So we have the potential energy and the distances of each molecular bond or interatomic distance. And what was noticeable was that the potential energy didn't change much at all, really. It kind of stayed the same even as we got into higher values or as time progressed. But what was most notable was the distances, the interatomic distances of the chlorite did increase as time proceeded. And that was just by the reaction itself here in these diagrams where we have our initial step and then the hypochlorite dissociates off and the distance increases as time proceeds. And then this graph again just represents that as time proceeds on, the distances increase further and further. And so moving from that, when we applied the wave packet to this, here we have it when the reaction doesn't surpass the energy barrier and is more suppressed. And then here we have enough initial momentum to surpass it and we create a product. And by this diagram, we see it moving off that since there's more of a scattering here, we have more. This is our product here. And then here we just stay as a reactant. Mm-hmm. And so how this affected our temperature and rates? Well, obviously, when we increased our initial momentum, our temperature increased as well as the rate of reaction, but the activation energy did remain constant since the potentials did not change very much at all. So really, we were looking at that transfer rate as we increased our initial momentum and how the distance between the hypochlorite and the heme increased as well. And so in this diagram is our activation energy barrier. And then this is the reaction proceeding forward. And then these are just small potential energies across the reaction itself. And so with my graphs here, the effects of temperature on rate, oops, my bad. There was kind of a linear progression with temperature and rate. So as our temperature increased, the rate of reaction also increased kind of linearly. This is our rate constant more so. And then with our Arrhenius plot, there was a nice solid regression line down the middle, which kind of showed a constant activation energy by calculation. And then with our probability distribution, this is what this looked like. The orange line here is our product, and the blue line here is our reactant. So as time proceeds, less of our product or less of our reactant is formed, or staying, and more of our product is formed, or the more likelihood of it forming. And then these two graphs are just two different showings of addition values and addition momentum. So the top one is a lower value, and so we see there is less scattering on top, which means there was less product, whereas here there is more scattering and there's more product formed. So basically what happened was my hypothesis of seeing the activation energy and potentials correlate was how I had expected, where the activation energy remained the same, and really what increased was the transfer rate and the distance between hypochlorite. And then also what was unique was the quantum tunneling that did appear. But for future works, I'd like to see this be more reconfigured, maybe develop some wells so we can analyze the potential energy more effectively, or just use wells to establish and see what happened there. With that, I will take any questions.
Okay, well, thank you. Anyone wanted to learn more about enzymes or challenge Bill with questions?
So your Arrhenius plot, when you do linearization, is it proper to add the highest energy or the lowest X value?
In this case, probably not. I did that more so just to see two different extremes and what was happening in the reaction.
Okay, because like the lower temperature was very linear, and then it like.
And then there was one up. Yes, that was just from as kind of an experiment to see what would happen at the extremes.
So then your like R squared value would get better if you exclude that.
Yes.
More questions? One. More questions, two. More questions, three. Let's thank Bill once again. And we are switching the gears once again sharply from biochemistry to the rocket science. So Joy Dahlgren will present a talk that will be liked at most by Joseph, because in his talk there will be literal proton transfer.
So at least this is the last day. I don't have to live up this far.
Oh, I don't know about that, bud.
It's going to follow me around.
Proton.
Alright, so I'm going to talk about the monomethyl hydrogen and nitrogen tetroxide combustion that's used for rocket fuel. So this is just a video of it in action on a loop.
I'm going to get the pro. 99, proceeded, 3, 2, 1, ignition. Right away, Houston. Vector good. X-side.
So it is, the combustion reaction is really good and produces a lot of energy, but it is extremely toxic for humans, so it's usually used for unmanned type rockets on or like missiles or some sort, if they're going that way. And then
Pipette is there for a reason. I don't want my hands anywhere near this thing.
It's really quick, and it is definitely very reactive.
You can really see there is this very fast reaction which generates loads of nitrogen and also ethane. And so all of the products here are gaseous, and you get a tremendous expansion. At the same time, because it gets very hot, it glows so brightly and produces a pipette is there.
So what were the components in this explosive stuff?
That's the monomethyl hydrogen, and then I think it's nitrogen dioxide to nitrogen tetroxide. So then the potential energy that's used to get this going is, it comes from, as the monomethyl hydrogen, these guys are oxidized by the nitrogen dioxide. And here's a little video of that happening. It's kind of showing it. So as these break apart and come together, that's those bonds breaking is what causes the energy. And then on this side is just the different energy levels that happens as the molecule is oxidized.
Not levels, total energy.
Total energy, I mean, yes.
And for specifically for Joseph, where is the proton that is getting transferred?
The proton that's getting transferred is
Which color for the proton is used?
It should be red, right?
Red is oxygen. Blue is nitrogen.
Yep.
What is color for proton?
The
Dark is
brown.
Brown is probably for carbon.
Carbon, okay.
What other colors are there?
White.
Okay, so white is for.
Oh,
carbon.
yeah, that's the hydrogen.
So,
yeah.
so which hydrogen is being transferred? Can you point by finger?
Should be right in this area. No.
There's a line.
Another. War. Yeah.
Oh, okay. Oh, yeah.
So
this
there
is
is
a-
a reactant, and what is the product? Just on same figure by finger.
Yep.
Product. Last image.
So
So where is this proton getting transferred to?
it's getting transferred to up here.
No, to oxygen, to red.
Oh, to the yeah. Yeah.
Okay. For positive guy.
So this is just setting up the code. So h bar is equal to 1, the mass of the proton in atomic units. This is the frequency of the proton's oscillation. P naught is what is being changed throughout the experiment. Width of the initial wave packet and the time step and the number of time steps. The more time steps would be a better representation, but it takes longer for the code to run. So then this is an example of the code running. I think this is about 30 momentum. So red is your reactance, and then green is your activation energy. Blue is your products. So as it goes on, products comes out, and it just, as the reaction goes, it settles out. This goes on for quite a while, but. So a big discovery when I was running the code is this reaction can happen at room temperature, as shown by the video earlier. So normally, under classical physics, your reactance isn't above the activation energy. So under classical physics, the reaction shouldn't go. But because of, I have a table of probability of the slopes, it's a non-zero probability slope. So the reaction does go. And this is due to quantum tunneling. So not as much of the reaction, you won't get as much products, but the reaction still goes due to quantum tunneling. And this is just the temperature and activation energy at various momentums. This is in this area, I should add more data points, but in this area, as the TEM, is when this will happen. So at room temperature and stuff, so in the 15, 16 momentum area. So then this is just the different momentum of graphs. So at 0 momentum, your electron, the probability where you find your electron is pretty straightforward. It's not really moving. And your probability of your products is very little. Reactance, so it's not going forward at all. And then this is just slowly as you increase the momentum, your probability of the reactant on your products is going up and reactance. And as you can see, the line on the bottom here, where you find the electron, is getting a little more curved, so it's moving more. And then this is at 3.1 momentum, as the slopes are increasing. And your position of where you find the electron is going away. And then this is quantum tunneling area as it goes. And then 6.2, so like I said, it just keeps increasing as the momentum increased and the temperature increased. So then this is where you start to see where the reaction will go as the slope of the probability increases, and you get your probability of finding the electron. And as it just keeps increasing, as you increase the momentum. And this is about where I have the highest probability and slope. As you can see, the slope is very deep or large compared to the other ones. And the probability of where you find your electron, it goes off. So as your products, reactants are turning into products. And then as you start increasing momentum past this point, it started to go back. As your slope starts to change less, it becomes lesser than that. And as you can see, it just keeps going as this turns back into more of a straighter line. Saying that, and then 80, and 90, and went back to it again. And then, so when you're at about 70 momentum here, it looks more like the momentum graphs at like 0 momentum, 1.87 momentum. It's more of a straight line. So you don't have as much product being, reactants and products being turned into. So that just kind of follows it, and then just kind of goes back and forth as reactants and products are turned as the momentum is changed. So that's the 100 momentum. And then this is just the slope of the probability of the graphs of these graphs. This is your products, so those graphs. And this is just the slope quantized. So as the momentum increased, your slope was increasing, meaning more reactants was turning into products. And this is right in this range is when you have a non-zero probability of the products, which means that the reaction still goes even though it's not above that activation energy. So that's due to the quantum nature of the particles going through. And that's about it. So.
Okay, let's thank you. So, questions? 100 atomic units of momentum.
Yeah.
Which temperature or which energy would it correspond to?
So that was, when you get that high, the temperature is like just ridiculous. So
how does it correspond? Yeah, sure. How does it correspond to temperature on surface of sun and temperature of nuclear explosion?
It's like similar to the temperature of the sun, especially when you're at this 40 momentum. I mean, that's 12,000.
It's about three times bigger.
Yeah.
3 times bigger.
Yeah. So I mean, you're never gonna get that.
So it means like your spacecraft lands on the sun.
Yeah, pretty much. So. Yeah.
Oliver has question.
So you flip between electron and particle. What is this actually simulating? Is it a proton transfer or an electron transfer?
Proton transfer. I say electron before. I didn't.
Yeah, sometimes.
Oh, sorry, my bad.
So
definitely proton.
What would happen if you were trying to use these simulations for any other atom in your system other than proton? So like carbon or nitrogen or oxygen.
So you would have more mass, which would affect.
Exactly.
Perfect answer. You would have more mass, so that would affect the kinetic energy and stuff.
So would you assume that the tunneling is still highly probable?
I would assume the tunneling, yes, because when you do it in real life, like the reaction still goes, and that's using nitrogen instead of just a single proton. It's probably not as probable at that large of a mass, but it still does happen. Yeah, that answers your question.
More questions to Joey? If not, thank you once again. And we have 20 minutes for 2 talks. So, Isaiah, his talk will be especially important for Alex to answer one of the questions. And now we are starting last but not least chapter consisting of 2 talks, which will be on the most complicated subjects. Before, everyone had either electronic motion or nuclear motion. Here, at some approximated level, will be simultaneous propagation of both electronic and nuclear degrees of freedom. So it is a big challenge, and even small step is a substantial achievement.
All right. So I had the photopolymerization of cyclohexadiene. What do I do? So you can see here, start with the product here, and then eventually we want to get to crystalline silicon. So CHS is a 6-membered ring, S6H12. And then it's first altered by UV radiation into its polymer form and eventually into the crystalline silicon. It undergoes a process called photo-induced ring opening polymerization. It has the ability to break the Si-Si bond to form our polymer. It can be used for many things. It's like the base material for microelectronics and photovoltaics. And it can be altered to produce semiconducting properties. These products have applications in microelectronics, transistors, circuit boards, and then eventually solar cells as well. Can improve our lives drastically. So my question that I started with was increasing the intensity of the UV laser, increase the average bond length, therefore assuming that it does undergo the ring opening property. All right. First here, you can see this is our ground state here going on, and then we want it to do to jump to the excited state through the radiation of the laser. Methods used, we use MATLAB. Code was ran using a lot of Dimitri's help. We have the initial Gaussian at time 0. The initial momentum was set to 0 as well. Then we altered the NTAL, which is time steps in the code, and then Rabi, which simulated our intensity of our UV laser, and then our expected bond length in angstroms is represented by this equation here. Just a side note, we weren't able to use to model exactly our silicon-silicon bonds, but the idea is very similar. So you can see here, this is just our initial position of our wave packet. It's just there, just as a reference. The green line here is our ground state potential, and then the tan line here is our excited state potential. And then the blue and red lines represent the probability distributions for the ground and excited states. So as you can see here, it begins stuck in the ground state here, and then the photo-induced jump to the excited state will happen here pretty quick. Then it propagates forward. Another issue we ran into here is that our window isn't infinite, so at the end there it will bounce back, which really isn't the best thing. You can see there at the end how it's grouping up over here. Results. So I used 10 different experiments, and then the NTAL to Rabi ratio is 1400. So I try to keep that throughout the entire section here. And then this is the average bond length in angstroms. I also have a graph over there. The most success was with our UV laser being set to 2, and our time step set to 700. It produces our largest bond length, and then assuming that it has the highest probability of dissociating out of the just breaking the Si-Si bond and starting to form a polymer. Then here are a few probability distributions. So right here we are seeing that there's no chance that it does get out of the ground state. You can see here it's stuck in the well. Rabi equals 1. Our time steps 1400. The one that I felt like had the most success, the video I showed, it is stuck in the ground state for a while, and then the photo-induced jump to the excited state happens here. And I got another one here. Intensity of the laser equals 5. Time steps 280. And then our UV laser is 14. Time steps.
Can you previous one?
Yep.
So at which time it promotes from ground to excited on the blue? At which time you switch the potential from ground to excited?
About 15.
Okay, and then you switch back from excited to ground?
Pardon me?
And then you switch, wave packet switched back from excited to ground. At which time?
Right about 50 here. It starts to jump back.
Or a little earlier?
What's
Like
that?
15 times 2, maybe at 30, when it starts deaccelerating, braking?
Okay. Right here.
Okay.
Yep, and then the larger I increased the UV laser, the more back and forth it was between the ground and the excited state. Got one more here as well. And then finally, in conclusion, I found that there was a really small window that I did find that did produce the highest probability that the bond length did break. The intensity of the UV laser may only increase slightly for it to work. And then through further applications and advancements, we can use these to improve our lives greatly. Microelectronics, photovoltaics. And yeah. Any questions?
Well, thank you, Sam. Before going to questions, let me ask you if I summarize your findings well. First, you didn't compute overall polymerization. You were trying only on the first step of like ring opening.
Yep.
And second, your finding is that you do not need very intense laser. You just need mid intensity for sufficient interaction.
Yep.
So questions to Isaiah? No one? Please.
So on your video,
yep.
The dynamics, I didn't really see where the wave packet went back to the ground state, and also I don't understand that the excited state seems to be lower in energy at that point than the ground state is. I'm confused what that means. You skip like halfway through.
Yeah.
The excited state is like the mustard color.
Yep.
So now it went underneath the ground state energy.
In this example, it doesn't transfer back to ground.
And then what does the Rabi mean?
Main question.
Just be the intensity of the UV laser.
Let me help.
Yeah.
It is how quickly it bounces force and back between ground and excited, and here it is like half cycle. Full cycle will be going up and down. Okay. More questions to Isaiah? Do not upload yet. Do not upload. There is a comment personally for Alex. It's the only chance, so it's personal message about your project. In the project that Isaiah was doing, the wave packet was completely propagated from ground to excited. But if it will be even lesser intensity of laser field and shorter pulse, it would promote only part of the wave packet from ground to excited and let it move. And then if after some time you can apply second pulse and promote another part of wave packet into the upper potential. And then you will create two Gaussian potentials in the ground state that may collide into each other. Make sense? Last chance to ask questions to Isaiah. If no, let's thank him once again. So, and last but not least, by Ben Jeffrey. He has exactly 10 minutes until we go off record. So, he will continue most complicated subjects in the course, simultaneous propagation of electronic and nuclear degree of freedom. Same as Kailyn and David, he will apply his knowledge towards perovskite materials.
but he will look onto not only electronic motion, but simultaneous change of interatomic distances and electronic state. Floor is yours.
Okay, so I'm going to be looking at infrared emission in perovskite quantum dots. So first, let's take a brief look at why you would want to study this. This is not worth it. So there's an interest in quantum dots for photovoltaic and light-emitting applications. It's growing every day. Many of these applications rest upon the infrared spectrum, communications, imaging. There's other ones I didn't want to list them. And so essentially, the more stuff we know about them and their properties in this range, the better stuff we can make. So take a look at the system. So we have this particular perovskite quantum dot. This is what it looks like. You can't really distinguish much of anything. So here's a better look. So we have like our lead right here, and our cesium, and our bromines, and the ligands surrounding it all. So, nice. And so the methodology is kind of based off of this idea where, the extension of where different bond lengths have different potential energies, and there's two different sets of potential energies, one for the ground state, one for the excited state, and we apply that to the one-dimensional case for one particular bond, a lead-bromine bond. Yeah. And so the blue is the excited state, and then the red is the ground state. And we put an electron in the excited state. As per that, with the Hamiltonian looking something like that. So Hamiltonian up and down refers to the Hamiltonian of the upper and lower states, which is what you would expect for a quantum oscillator. But H up, down, and H down, up are diagonalized spring constants for the ground state. And these are the non-adiabatic approximations of the coupling between the two states. And this assumes that the transition occurs so quickly that no movement of nuclei occurs during the transition. So, got that right. So, here's just an example of, here's the emission expectation value. It's based off the difference of energies of the levels. So this one. So here's an example of the dynamics that occur. The blue is the excited state, and the red is the ground state. We can see it kind of goes back and forth between the two. This is for one particular momentum. I guess I should have mentioned that I'm changing momentum. That's kind of important. But, so yeah, don't need to watch the entire thing. Here's some results. Tables are boring, so let's look at some prettier results. So we have a table. We have our initial momentums and recombination rates. We'll see it's roughly quadratic for this area of initial momentums. And then looking at emissions, like the emission wavelength, it's fairly stable for lower momentums, but as we go to higher momentums, it's a bit more varied. So here's just some dynamics information for initial momentum set at 5 and initial momentum set at 100. So Yeah, I guess.
So what are those blue and orange spotting?
Blue is the probability of the electron in the excited state, and orange is in the ground state. Kind of oscillates between the two in lower momentums, but in higher momentums it just kind of spreads out a bit. Yields get a lot more jagged as momentum increases as well. And so, two main conclusions that I drew from this. Infrared emission rates peak at lower temperatures, specifically 5 atomic units of momentum, or 27 Kelvin. And wavelength of emission is fairly consistent at lower temperatures from about 0 to 100 Kelvin and grows more varied as temperature increases. So.
Okay, let's thank Ben. Any questions?
So can you go, I think it's back like 3 slides, where you have the graphic of, yeah, this one. Sorry, bit here. What is the emission micro, is that meter?
Yes, that's micrometers.
How do you have a negative micrometer?
I was wondering that as well, to be honest. But whenever I searched up like negative emission, all I got was like carbon, like negative carbon emissions, like greenhouse gases and stuff. So, yes. Okay.
Can I try to help?
Yeah.
It's really either very bad error or very big discovery, but maybe hypothetical. At some amplitudes, the potential surfaces cross, and they swap the order of excited and ground.
Okay.
And then the sign flips. And if you just want to wrap out mind around it, then you just change from absorption to emission. Just energy goes different direction.
And then for the rates, can you use Marcus theory to get rates?
This was using Marcus theory. I guess I didn't explicitly state that.
Okay.
No?
What we can do, he used parameterization similar to Marcus theory.
Okay.
But not the rate based on Marcus theory. More questions to Ben? Okay, let's applaud how brave he is and please give me stage for a second.
That's fine.
So there were presentations in 4 chapters. You saw that the physical chemistry knowledge applies to a very broad range of applications, from rocket science to biochemistry, and many thanks to visitors and everyone who contributed into discussions and questions. With this, we finish all activities related to the course. The participants of the course will soon look into the online grading system, and I guess they will be they will be positively impressed by their grades.
So we all pass.
So with this, let's thank everyone and complete all activities for the class.
I thought he was going to say not so impressed, and I was like, that's great.
There was punishment right here.
Oh, there was plenty of clementines back here.
Clementines are the best.
Just how many clementines you and Michael?
It's like 4. Didn't really have
It's like a whole
breakfast,
jug
so-
of, it's like a whole jug of orange juice right there.
What? I'm not expecting somebody